In this video, I will demonstrate the Lagrangian method of constrained utility maximization. We've seen how graphically consumers, when faced with a budget constraint, will choose a consumption bundle that is both on the budget line and at a point of tangency between an indifference curve and that budget line. Let's now look at how we would write this problem mathematically. This is what we call a constrained optimization problem, where the goal or the objective is to maximize utility, and the constraint is that consumers have to stay within their affordable set or their budget set. It's important that you understand that even though we're going to do a mathematical approach of this, the optimum that we're going to get is still going to be the same as what our graphical analysis said, and that is consumers are going to choose a bundle where their MRS, the slope of their indifference curve, matches their MRT, or the slope of their budget line. That is, consumers are going to choose an indifference curve that's tangent to the budget line. One approach to doing this math is called the Lagrangian method. The Lagrangian method is a way of taking the objective function, here the utility function, again the objective is to maximize utility, taking the objective function and the constraint, the budget constraint in this case, and combining them into one equation that then itself has to be maximized. So that one equation is called the Lagrangian equation, and you see it here on the screen, where the Lagrangian equation is set up as being equal to the utility function plus lambda, which is called the Lagrangian multiplier, and then times in parentheses income minus the expenditure on X minus the expenditure on Y. For now, just think of lambda as a mechanism of combining the constraint, the budget constraint, and the objective function, the utility function, into one equation. Now the goal is to choose values of X, Y, and lambda that makes this Lagrangian equation the biggest it can be. We want to maximize the Lagrangian equation. You learn in calculus that anytime you're seeking the maximum of a function, or the minimum for that matter, you're going to look for where the slope of that function is 0. Well, in this example, we have 3 different slopes because we have 3 different variables. For each of the variables, x, y, and lambda, we can look at the slope of the Lagrangian equation. Each of these slopes is a derivative, or more specifically a partial derivative, and at the maximum of a function, all of these partial derivatives will be simultaneously set to 0, and we call these the first order conditions. What you'll see next through example is how we can use these 3 first order conditions to solve for the 3 unknown variables of x, y, and lambda. That is, we have a system of 3 equations in 3 unknowns that we can use to solve for those unknowns. Again, importantly, you'll see that this method is still going to give us 2 conclusions that we saw from class on Monday. The first is that you're going to get at the optimum equal bang per buck from goods X and Y, and you're going to get at the optimum a point of tangency between an indifference curve and a budget line. I think the best way to learn this is by example, so here we go. Let's say we have an individual whose preferences are represented by a Cobb-Douglas utility function. This individual has an income of $20. She faces a price of X of $10 and a price of Y of $5. The question now is, given her budget constraint, what combination of X and Y will she select? I could have asked this as, what's her utility maximizing combination? Or what's the point at which her indifference curve would be tangent to her budget line? The first of 3 steps here is going to be to create the Lagrange equation. The Lagrange equation is always going to be set up the same way. It's going to be L equals the utility function that's given in the problem, plus lambda times parentheses income, as given in the problem, minus the price of X, also given, times X, minus the price of Y, also given, times Y. In this example, the utility function is U equals X to the 1/2, Y to the 1/2, so that gets plugged in for U. And in this example, income is 20, P of X is 10, and P of Y is 5. Step 2 is to take the first order conditions. That is, for each of the three variables, x, y, and lambda, partially differentiate the Lagrangian equation with respect to that variable, holding the other variables constant, and then set those partial derivatives equal to 0. Now, it's important that you understand that first order conditions are the partial derivatives equaling 0. If you just write for the first order conditions the partial derivatives and don't set them to 0, you're not really expressing an optimum. You're just giving me derivatives. So when I ask you for those first order conditions, make sure that each partial derivative is set to 0. Now what we have, and you can see here the partial derivatives for this specific example. Now what we have is three equations with three variables. So the third step is going to be to solve this system of equations. There's two methods I want to show you, both of which are valid, and each of which leads us to a familiar conclusion. So here's the first method. I'm going to take the first order condition and solve it for lambda. I'm going to do the same thing for the second first order condition. I'm going to take it and solve it for lambda. Then what I can do is say, well, lambda equals lambda, so I've got this equation here. I did that because I'm trying to take my three equations and three unknowns and whittle them down to solve for those unknowns. So by setting lambda equal to lambda, now we've got lambda out of the way, and that allows us to write y in terms of x. In this example, the math becomes, once I simplify using fraction rules and exponent rules, in this example the equation becomes y equals 2x. What does that mean? Well, that means that the optimal bundle, this consumer, will choose to buy twice as much y as she will buy x. Her chosen amount of y will be twice as much as her chosen amount of x. But I don't know what values y and x take on because I have an equation with two unknowns. In order to solve that equation with two unknowns, I need another equation with the same two unknowns, which I have right here through the third first order condition. Now that I have two equations with the same two unknowns, I can solve for those unknowns. One way of doing that is to make a substitution. Where there's a y in the third first order condition, I'm now going to substitute y as 2x. Now my equation only has x in it, and I can find that x is 1. Given that y is 2x and x is 1, y is 2 times 1, which is 2. And that's the answer here. Given this individual's specific Cobb-Douglas utility function and given the income she has and prices she faces, her best decision will be to consume 1x and 2 y's. One thing that I want you to see from this method is that what we have going on right here is equal bang per bucks from x and y. Take a look. The numerator right here, 1/2 x to the minus 1/2 y to the positive 1/2, is exactly mux. The denominator here, 10, is exactly p of x. So this side of the equation is mux divided by p of x, or the bang per buck from x. Likewise, on the right-hand side, the numerator is exactly muy, and the denominator is p of y, and so the right-hand side is muy divided by p of y, or the bang per buck on y. What this method of solving the system of equations gives us is that at the optimum, consumers get equal bang per buck from goods X and Y. Let me show you another strategy. The other strategy starts the same. It sets up the Lagrangian as the utility function, here x to the 1/2, y to the 1/2, minus lambda times income minus p of x minus p of y. It also then takes the first order conditions where each first order condition is a partial derivative and where all are simultaneously set to 0. How this method differs is in how the system of equations is solved. Here what I'm going to do is take the first order condition, and I'm going to pull the minus 10 lambda over to the right hand side. So now I've got 1/2 x to the minus 1/2 y to the 1/2 equals 10 lambda. I'm going to take the second first order condition and pull the minus 5 lambda over to the right hand side. Now I've got 1/2 x to the 1/2 y to the minus 1/2 equals 5 lambda. Then I'm going to stack one on top of the other. Doing that is going to, like the previous method, allow me to get rid of the lambdas, because on the right hand side I have a lambda in both the numerator and the denominator, and so those lambdas cross out. Doing this also allows me to more readily simplify the left-hand side, which in this case becomes a y over x. What I want you to see here is that what we've done here is essentially setting the marginal rate of substitution equal to the marginal rate of transformation. From this equation we can solve for y, and that's exactly the same equation for y in terms of x that we got from the previous method. This tells us the consumer is going to choose to buy twice as much y as she does x. And then to find those values of y and x, we're going to plug into the budget constraint, which is exactly the third first order condition. Doing the following math gives us the same result that in this example, the best bundle she can buy, given her budget constraint, is 1x and 2 y's. So in summary, one approach to solving a constrained utility maximization problem is called the Lagrangian method, where you first set up the Lagrangian equation, then you take the first order conditions, and in doing that, you see that you get the same two results from the graphical approach. That one, at the best bundle, the optimal bundle, consumers get equal bang per buck from x and y, and two, at the optimal bundle, the indifference curve has a slope in absolute value that matches the budget line slope in absolute value. In this video, I will demonstrate the